bivariate data. So this topic is full on calculator. You definitely have seen these before. Let's do a quick recap. So the x-axis has the independent variable, or what you change, and the y-axis has the dependent variable, what you measure. Now, this is an example of a positive correlation where there is an outlier, and we draw a line of best fit, which we're going to look at in a second. Which this line of best fit is linear in this case. You could have a line which is non-linear. It could look somewhere like this, a curve. Now, this would be a negative correlation, and this would be no correlation if all the points are all spread out. One last thing, there's a difference between correlations and causations. So there is a correlation, believe it or not, between shark attacks and ice cream sales. This is probably because summertime there's more likely to be shark attacks because more people at the beach and people buy more ice cream, okay? So they do have a correlation, but a correlation doesn't mean causation. It doesn't mean one thing causes the other. So because even though there's a correlation, it doesn't mean shark attacks cause ice cream sales or that ice cream sales cause shark attacks, okay? So that's the big difference. Moving on to Pearson's product moment correlation coefficient. This requires a calculator. So PPMCC ranges from -1 to 1. That's the range. The positive correlations can be as big as r equals 1, and the negative correlations can be as big as r equals -1. 0, if r equals 0, it essentially means that there's no correlation. So r is the correlation coefficient, and the points must be somewhat linear for you to consider using this method. So in this case, we have a weak positive and a linear correlation. This means that r is going to be something like 0.3 if we make an estimate based on what it looks like. If the points were perfectly lined up in a straight perfect line, the correlation would be r equals 1. Now, looking at a negative correlation, we can see that this one is moderate. It's not weak, but it's not very strong either. It's negative and linear. So r, if we make an estimate, could be around -0.6. Again, if the points were lined up perfectly and were negative, r would be -1. During an exam, you'll be given a table such as this one, which you're going to use to figure out the correlation coefficient r. First, in the main menu, you're going to go to Statistics here. Okay, and you're going to fill in the two columns. So list 1 is going to be my weight, the x values, so 0, 10, 30, 50. We're going to write down the 10 of them. And when we're done with that, we're going to move on to list 2 and go ahead and write down the y values, in this case the length in centimeters. So that's it, 0, 0.5, and so on. And after that, we're going to go to a certain menu that's going to give us the r values. Okay. Why is this taking so long? Okay, it's basically done now. Great. Now, we've plotted all the values. We go to graph 1, press F1 trace, then press it again, calc. That's right. Then X, F2 zoom, press it again, and here you can see the R value is given to you right there. Now looking at regression lines, so we've finished these two topics. A line of best fit is only appropriate if R is larger than 0.85 if the correlation is positive. Now, if it is negative, this isn't the best drawing. If it is negative, it needs to be smaller than -0.85. Okay? Remember that the largest value R can be is 1 for positive correlations and -1 for negative correlations. So it needs to be pretty strong in order for you to draw a line of best fit. Now, if you are going to draw one, you first need to calculate the mean X values and the mean Y values. How to do that? You add all the X values together and divide them by the number of X values, and same with the Y values. You should know how to calculate the mean. So if the mean is 10, 27, for example, and these are different points in the graph, this is the point. Well, the line of best fit is going to go through this point, okay? It goes through the mean point. Now, there should roughly be the same amount of points above and below this line, and again, it should go through the mean point. Now, that was fast. Let's look at the different poles that we might have in a scatter graph. So the lower pole is the line that goes through the vertical line that goes through the smallest value, and the upper pole is the vertical line that goes through the biggest value. That would be the upper and the lower pole. Interpolation is the space between the poles, and extrapolation is all the values that are below the lower pole or above the upper pole. The regression line calculation is going to be pretty simple to calculating the correlation coefficient R. So you're going to plot in the X values on the first column and then the Y values on the second column, the list 2, and you're going to go to the same place. So graph 1, F1, calc, F1, now F2, X, press it again, and boom, you've got the formula right here, Y equals A plus BX, and the A and the B value. So it gives you these two. All you've got to do is substitute them into the formula, okay? And that's pretty much it. Lastly, we've got the Pearson's rank correlation coefficient. Now it's going to be similar to PPMCC, but there's going to be a slight difference at the start where we're going to rank the values, as you're going to see in a second. When to use SSRCC, when to use PPMCC. So the difference is whether the relationship is monotonic or not. So this means that it increases or decreases, but is not necessarily linear. This line right here decreases, but it's not linear, and so it is monotonic, and so you use SSRCC in this case. PPMCC is for linear relationships, okay? They must be linear, and they must increase or decrease. So as always, you're going to be given a table, and in this case, you're always going to have to rank the values from biggest to smallest for each column. So the best taste was a 5 for juice, and so it's the biggest value, and we're giving it the rank number 1. The smallest value, on the other hand, is the taste of 1 given to chocolate. Okay, I'm surprised by that. And so it's the worst value, it's the last value. How many values are there? 5. So it's number 5 in the list. Okay, and you do the same for values for the Y ranks, and that's what you're going to do always. Okay, this is very important. This time you're calculating R sub S, not just R. Let's have a look. As always, you go to statistics and you start filling in the table. So first column, 4 for X, okay, then it's followed by 2, by 5. I'm filling this in. Now list 2, 4 goes with 1, and then 2 goes with 3, and so on. Okay, now we're doing this, and the process is the same as PPMCC from now on. We go to graph 1, calc, X, then again, and R is what we're looking for. Okay, so R in this case equals 0.2. Remember that it's R sub S. The only difference is that we're going to rank the values and plot them in the table, not just plot in the table straight away. Now, what if there's a tie, as you can see right here? What if two values are the same? So how do you rank them? we're looking at this y column, okay? So if we rank them, we'll see that number 8 in y is the largest one, so it gets ranked number 1. And then 7 and 7 are the 2 and 3 respectively, but they're the same, so how do you decide which one is 2, which one is 3? You don't. What you're going to do is find the midpoint, okay? So what's between 2 and 3? 2.5. If, for example, the values are like 12.5 and 67.3, how do you know the midpoint? Well, you add them together and divide them by 2, okay? So in this case, we add them together, divide them by 2, and it gives us 2.5. And so both of them are going to be 2.5, okay? So this is going to be 2.5, and this is also going to be 2.5. Excuse my writing, it's not very good, okay? And that's all you would do if there's a tie.